Welcome to Lesson 7, which is Applications of Differential Equations. This lesson is actually going to be broken up into two parts, with the first part being to formulate and use differential equations including natural growth, radioactive decay, and population models with systematic addition, removal, and population. Natural growth models. In many modeling situations, the rate of change of a variable y is proportional to the value of y. Given y is a function of time, t, the proportionality relationship is expressed as dy dt equals ky, where here is our rate of change, and this is proportional to y by writing ky. The general solution of this differential equation is given below. Invert the differential, which results in dt over dy equals 1 over ky. That allows us to integrate both sides with respect to y. So we're writing both of our integrals with respect to y. This yields t equals 1 over k ln y plus c. Step 3 is to make that y the subject. So if we subtract c from both sides, and multiply both sides by k, we have k outside of t take c equals ln p. We can now write that as an additional equation. That's base e, so e to the kt take c equals p. If we use our index laws, we can split this up, which would be e to the kt multiplied by e to the negative kc. Remember, if you're multiplying, your index laws say to add these two. If you add these two, you end up with this exponent. Hence, the general solution to our differential equation is p equals a e to the kt, where this thing here, when we actually find out some initial conditions, is a. So a equals e to the negative kc. A city with population p at time t years after a certain date has a population which increases at a rate proportional to the population at that time. If the initial population was 2,000, and after 2 years the population had risen to 2,400, calculate the population after 5 years. Step 1. Write a differential equation where p is population and t is time. So because we're saying it's proportional, the rate's proportional to the population at a time, we can set up the differential equation dp dt equals kp, which, as we know, we can rewrite or invert. Step 2, solve the differential equation. Taking the integral of both sides with respect to p, we have t equals 1 over k outside of the integral of 1 over p dp. And this is going to be ln p. This is going to be 1 over k, so we end up with 1 over k ln p plus c. Now we rearrange and subtract c from both sides, multiplied by k. We have ln p equals k outside of t take c again. Rewriting that, we have p equals e to the power of this, which is the general solution of a e to the kt, where a is that initial e to the negative kc. Step 3 is apply the given data to develop a suitable model. So we have p equals a e to the kt. Initially, we have 2,000. 2,000 is our a, and if we want to find out the parameter k here, we can sub in 2, because at 2 years later the population was 2,400. So if we let p equal 2,400 and sub in a 2 for our t, we can now rearrange. So we divide both sides by 2,000, take the natural log of both sides, and then because of this 2k, we'll divide by 2. So k equals 1/2 ln 1.2, which is approximately 0.0912. We now have our model, which is 2,000 e to the 0.0912 t. Hence, I can actually find out the population after 5 years, which is to sub in 5 for our t, evaluate that with a calculator, and approximately 3,155 people. That's an example of using differential equations to model and solve problems in real life. Radioactive decay is a different type, but still has similarity to the previous example in terms of exponential growth in the form of a e to the kt. So radioactive decay is measured in terms of half-life. The number of years required for half of the atoms in a sample of radioactive material to decay. The half-life of some common radioactive isotopes are as follows. Here's a list of some common ones that we'll use in our examples: uranium, carbon, radium, plutonium, etc. And here is the half-life in years. The general rate of decay is proportional to the mass of the radioactive substance present. Hence, the mass, dm, dt, or the rate of change with time, is proportional to negative m. Therefore, a differential equation is dm dt equals negative km, where k is greater than 0. So it's pretty similar to our previous example where we had km. This time, because of decay, it's negative km. The general solution to this type of differential equation, as I said, could be y equals a e to the negative kt. In this case, mass equals the initial mass multiplied by e to the power of negative kt. Example 24. Suppose that 20 grams of plutonium isotope Pt.2 was released in a nuclear plant accident. Determine how long it will take for 20 grams to decay to 1 gram. Step 1. Write a differential equation where y is the isotope in grams and t is time. So, because our rate of growth is proportional to the amount present, our differential equation is dy dt equals negative ky. We're not going to solve this equation as done in the last example, but rather use a general solution. That is, y equals the initial value of y, which is y naught, e to the negative kt. Step 3. Apply the given data to develop a suitable model. Because you know the initial amount of radioactive isotope is 20 grams, y naught is 20. Hence, we have an equation, y equals 20e to the negative kt. To determine the value of k, we need to use the half-life table. And as 20 grams will, in terms of its half-life, then become 10 grams. So we want to know how long it takes 20 grams to then decay into 10, knowing that the time to do it is 24,065 years. We divide both sides by 20. Now we have an exponential equation to solve using natural logs. The natural log of 1/2 equals negative 24,065k, which means we can divide both sides by that number, negative 24,065. And k equals the exact value. In terms of to a very small decimal places, we have negative 0.00002888032t. That's our general solution or our equation to model the exponential decay. Determine the time it will take for the sample to decay to 1 gram. Let's let y equal 1. We now divide both sides by 20. Take the natural log of both sides, then divide both sides by that k value. Our time is approximately 104,000 years. Difference of rates. Consider the following. Population models with regular removal, e.g. the population is growing naturally, but X objects are removed each period of time. So maybe at the end of every year, you remove 10 of your species. Or an object is being heated up at the same time cooling, or liquid is being added to a container that has a leak. So you might have a leak of 10 litres per minute, but you're adding water at 11 litres per minute. Example 25 is a farmer initially has 400 goats. The number of goats increases at a rate of 20% per year. Each year, the owner sells 50 goats, so that's the regular removal. Write a differential equation and modelling the number of goats, and solve the differential equation and determine the number of goats after 10 years. Step 1, write a differential equation where n is the number of goats and t is time. Here, k is 20%, so therefore, it's written as 1/5 or 0.2. The n dt equals n over 5, take 50. So there's our rate, but we're taking out 50 regularly each year. To simplify this, write it with a common denominator, so that would become 250 over 5. We have dn dt equals n subtract 250 over 5. Step 2 is to solve the differential equation. Given dn dt equals n take 250 over 5, we want to invert both sides. By doing that, we can then integrate both sides with respect to n. In doing so, we're going to have t equals 5 natural log of n take 250 plus c. Note that n has to be greater than 250 here. Step 3 is to calculate the constant integration. If we sub in initial conditions, which is t equals 0, we had 400. We then have 0 equals 5 ln 400 take 250, which we simplify and rearrange. C, we want to isolate, would be negative 5 ln 150. So I've just rearranged. Step 4, rearrange and solve for n. Here, if we have 5 natural log of this, subtract 5 natural log of this, we can factorize out the 5. Now we have a natural log, subtract another natural log. So using our log laws, we can write the natural log of n take 250 divided by 150 equals t over 5. Because here, we divided both sides by 5. Hence, it'll be e to the t on 5 equals n take 250 over 150. Rearranging, if we multiply both sides by 150, then add 250 to both sides, we have our model here for the number of our animal with respect to time. Step 5 is to determine the number of goats after 10 years. This is simply subbing in 10 to t. In that case, using function notation, using a calculator, it's approximately 1,359 goats. To test your understanding, you can try the following question. Suppose that 16 grams of a radium isotope decay over time t. Determine how long it will take for the 16 grams to decay to 5 grams. Note the half-life for that is approximately 1600 years.